EMF, we have seen that how to identify potential difference or EMF across a rod while it is linearly moving in the magnetic field. Now let us see that if a rod is there, okay, so it is rotating inside the magnetic field. So everywhere magnetic field is there, something like this, and it is rotating about one end. So it's completely magnetic field is filled in this region. It's a uniform magnetic field, which is the direction is into the border, and this rod is rotating with angular velocity omega. So here it is instantaneous. If omega is increasing, the potential difference also keep on increases. If omega decreasing, potential difference keep on decreases. So I am talking about for a particular omega. So if it is rotating with angular velocity omega, length of the rod is L, then I want to identify what is the potential difference across the ends. So here I am taking that A is one end or C is one end of the rod and D is other end of the rod, and it is rotating about axis of rotation passing through D and perpendicular to rod. So this is axis of rotation, means axis of rotation is parallel to magnetic field. Now this is the scenario, and we are going to find out motional EMF for rotating rod. Now we know that the potential difference across a small part is V bar cross B bar dot DL bar when a small part of the rod is moving linearly inside the magnetic field. But here length of the rod is L, which is not a small, but it is a straight and rotating with angular velocity omega. Now what I do is randomly I take a small part of length dx at a distance of x from the axis of rotation. So this is the dm. So why I am taking the very small part? What is the reason behind it? Is we know that if I am taking any object is rotating, pure rotating, if I take any small part of that rotating object, that will go linearly. At every instant it will have some linear velocity. So from that idea, from that linear velocity idea, so I can end up with some EMF across that small part. So that was my idea. Let us see. Now this is the small part dx at a distance of x. Then this small part will have the velocity, which is exactly perpendicular to length. That velocity will be x omega because it is rotating with omega. Then x is the distance from the axis. Then x omega will be the velocity. So if I take a small part of length dx is having the velocity x omega, magnetic field is inside. The magnetic field and velocity perpendicular to each other. Even length and velocity also perpendicular to each other. So length and velocity perpendicular, magnetic field perpendicular. Whenever these three are mutually perpendicular, we know that the potential difference across the small part is equal to VBN dl. You can write down VBDL, which was earlier we derived this part. This one dV is equal to, now velocity is equal to x omega, magnetic field is B, and length of the small part is dx. So ultimately this is the potential difference across the small part of the rod, but we require potential difference across the entire rod. That means if I consider rod into different small parts, potential difference across the first part, second part, third part, and so on, if I add, I'll get the total potential difference across the rod. So net potential difference, this is not potential, it's a potential difference, or EMF across the rod. Potential difference across the rod, any terminology same, is equal to integral dV, which is integral B omega x dx. Same thing I am writing. Okay, from x value changes from 0 to L. So x value is 0 to L. So I will get B omega x dx is x square by 2, 0 to L. Then I will get B omega L square by 2. This is the EMF across the rod when it is rotating. But remember, this formula you can directly apply whenever rod is rotating about an axis perpendicular to rod and passing through one end of the rod. Whenever it is one end of the rod, you can apply this. Now this is the magnitude of potential difference across the rod. But the question is, which one is at higher potential and which one is at lower potential? Now again we use the palm rule. We keep the thumb in the direction of velocity, remaining fingers in the direction of the magnetic field. then upper side of the palm will have higher potential. So C will be at higher potential positive and axis will be at lower potential negative. So that means electrons will move towards the towards the axis of rotation. Then positive charge will accumulate away from the axis of rotation. So like this we can identify potential difference or EMF across the rod. Now I am taking the rod. Now this rod is not rotating about one end. It is some random axis I am taking. This is the axis of rotation. So that rod is rotating with angular velocity omega inside the magnetic field. Everywhere magnetic field is there. Okay? Everywhere magnetic field is there. Now we want to identify what is the potential difference across the magnetic field is B. Potential difference across the C point and D point. O is the point where it is, about axis passing through O point perpendicular to rod. About that axis, this rod is rotating with angular velocity omega. Now again, actually we need to find out the potential difference across the C and D. Again we have to do the integration method, but no need of it. Already we know that. Already we have one formula. Whenever rod is rotating about an axis passing through one end, rotating with angular velocity omega, length of the rod is L, then potential difference will be B omega L square by 2, and at the axis negative potential, low potential, at the end it will have higher potential. So same logic we apply here. So what we do is we split the rod into two parts. I am supposing that length of this part is L1. See, it's a random calculation. You may be asked anyway. In the question they may give you this is 2L by 3 and this is L by 3, or L by 2, L by 2. Anyway you can give. So that's why I am taking the random. This length is L1, this length is L2. Then total length of the rod will become L1 plus L2. Okay? So then, now potential difference across the C point and O point. I can write down like this. Potential difference across the C point and O point. I am writing as potential at C point minus potential at O point is equal to, as I am taking this is the part of the rod, neglect this part. Now this part is not there. So it is equivalent to this part. According to the, this formula, okay, we can write down the potential difference across this part. Because here also axis passing through one end of the rod and perpendicular rod. The rod is rotated with angular velocity omega. So then Vc minus V0 is equal to, I can write down B omega same, but L value will become L1 square by 2. This is Vc minus V0. So I wrote this is at higher potential because moving with velocity V. Okay. So keep the thumb in the direction of velocity, fingers in the magnetic field direction. C will be at higher potential, O will be at lower potential. Now take the OD. Now you take the only lower part. No need of upper part. Now you can take like this is one rod rotating with angular velocity omega. So again it is angular velocity V. Remaining fingers in the direction of magnetic field. Then D will be at higher potential. Upper side of the palm means this. Okay. So D will be at higher potential and O will be at lower potential. Then I can write down the potential difference across these two ends. VD minus VO is equal to length of this part is L2, so V omega L2 square by 2. Now we want to find out VC and VD, which is at higher potential. If L1 is more than L2, then VC will be more than VD. L1 is more than L2 stands for VC is more than VD. Then under that condition, I can write down if I subtract these two, VC minus VD is equal to V omega L1 square minus L2 square by 2. That is the potential difference across the rod. If rod is rotating about at random axis, you can split the rod, you can identify potential difference across the rod. Sometimes they will give you that there is a ring. This is conducting plane. So I tell you what is the importance of this conducting plane. This is a conducting ring. This ring is rolling without slipping. Sometimes to confuse you or to make you afraid of the question, then they'll give you like this. Ring is moving with velocity v and rotating with angular velocity omega, and this is pure rolling, no slipping anywhere. It is purely rolling motion. That means V is equal to R omega, you can identify. Now we want to identify the potential difference across A point and B point. Let us say this is C and D, because we have to apply the magnetic field as B. Magnetic field is B. Radius of the ring is R. Okay. Across C and D points, we want to find out the potential difference. Now what I have to do is, see, if I am taking as a ring as a whole, here one important thing to remember. If I am taking the total ring, then the flux through total ring at any place is equal to, the flux value is equal to B into pi r square, which is constant. So flux does not change. As flux is not changing, then EMF in the ring will be 0. EMF in the ring is 0. So net EMF across the ring, inside the ring, will be 0. No current will be developed. But we are asking the potential or EMF across the C point and D point. Suppose that this is the conducting plane is grounded. Grounded means D point potential will be 0. Now we want to identify what is the potential at C point. Potential at C point can be there. Even though ring is not having any current, still we can get the potentials. How? Let us say a circuit, simple circuit. Suppose that I am taking the one battery like this, and one more battery I am connecting in this way. Okay, positive connected. Both the batteries are having the same EMF and same internal resistance. Identical batteries are connected like this. Under this condition, then you will find net EMF will be 0. If you want, you can apply Kirchhoff's law. You can start from A point. This is the B point. C, obviously B and C should have the same potential. A and D should have the same potential. Then if I am moving from A to B, then minus E. So current is, suppose that I, you can take anywhere, current is I like this, because here current is 0. You can take any direction, it doesn't matter. Okay. Now I'm going opposite to current. So plus IR and opposite to current plus IR again. Now negative to positive plus E is equal to 0. E cancel out. Then 2IR goes to 0. Then I value goes to 0. So current in the circuit is 0. But batteries are there. EMF is there. Potential also will be there. Suppose if I am taking the B as grounded, that means 0 is the B potential. Then A potential will be E. So current is 0. EMFs are there. Then still you will get the EMF for a particular point in the circuit. A similar concept you can apply here. So ultimately EMF in the entire ring is 0. EMF in the total ring is 0. If I am taking the conducting plane is grounded, then potential at D point goes to 0. But we cannot say that potential at C point is 0. Okay. So this is a doubt. We have to check. We cannot say potential at C point is 0. There can be some potential. We can identify. Okay. Now what I am doing is I am taking the only CD part. If I take the CD part, then the CD part will have, every point of the CD part will have different velocities. What are linear and tangential velocities will be there. But as it is no roll, rolling without slipping, I can take, if I am taking, here this is the axis of rotation. I am taking the axis of rotation here, which is called as instantaneous axis of rotation. With respect to instantaneous axis of rotation, the ring is in purely rotating motion. It exhibits pure rotatory motion. Whereas if I am taking the axis of rotation passing through center, it will exhibit rolling, which is combined motion. Okay. So I am taking the axis of rotation at the bottommost point, then ring will exhibit pure rotation with angular velocity omega. Now I am taking the only half of the ring, then EMF does not depend on the shape of the ring, it depends on the only line or end points. Now I am connecting the end points C and D points. Then the length of the C and D will be 2r. Now something like a rod of length 2r is rotating with angular velocity omega. Okay, about one end. Then what is the potential difference? BCD is equal to B omega 2r whole square by 2. Then BCD is equal to 2B omega r square. As I have taken the potential at D point is 0, potential at C point is equal to 2B omega R square. So there is the potential C point. So EMF on this side and EMF on this side, both will create same EMF you'll get. So both the EMF will cancel out, the net EMF goes to 0 and net current in the circuit goes to 0. So for more videos, please subscribe and hit the bell icon, and you can see the playlist. There you will find more number of videos. You can go through the different type of questions.